Welcome to This Week in General Chemistry 2 Laboratory. This week we're going to do the determination of phosphorus in plant fertilizer by gravimetric analysis. So, in commercially made products that contain phosphorus for fertilizer, there are ways that we can check to make sure that the advertised value is the same as what's actually present. One of the reactions that's done is this one, where we can actually take the phosphate as hydrogen phosphate and in solution react that with ammonia and magnesium to make a magnesium ammonium phosphate precipitate. That precipitate is a solid. We filter that from the solution and then we mass that, and so hence gravimetric analysis, we're doing the measurement by weight. All right? We're going to take the value that we find experimentally and do a percent error calculation to compare it to the value given by the manufacturer. So this would be a way to quality control the phosphorus in the fertilizer. And so gravimetric analysis is a standard technique in analytical chemistry, and using mass, which is one of the most accurate ways to weigh, to find the amount of material present. And so in this case, we're actually doing it for the phosphorus. Now, it always involves some math because the compound that we're precipitating is a magnesium ammonium phosphate with 6 waters in its crystalline form. And so we'll have to do stoichiometric calculations to get to specifically the phosphorus that's present. The experimental for this lab is very straightforward, and it will actually take a week, so it will be due in 2 weeks. It takes a week to dry the solid. All right. So anyway, I'm going to talk a little bit right now soil formation. Most of the natural phosphorus comes from 2 places: weathering of rock and then decomposing plant matter. And so in a normal setting, then those things would be in a cycle in which the phosphorus is being reused as plants and animals decompose and are done with it. And then, of course, natural processes weather rock, and if it has phosphorus present, then it becomes available at that point. But what we do is we end up with phosphorus in the soils, right? And so the topsoil, in terms of a horizon and a picture of that, is where we would primarily want the phosphorus to be available for plants and those types of things. Some things deep a little bit root a little bit deeper than that. And so anyway, but that phosphorus would be available in that top region. And so anyway, if we look at that nutrient cycle as I was referring to in a couple slides ago, then elements in organic matter and in animals are processed. They end up in the organic matter in the soil. Through decomposition, the minerals are freed, and then those are in solution, pulled up into the roots, and then incorporated into the plants. And then we get our phosphorus from the consumption of the materials that are in our food, which were produced by our autotrophs. And so anyway, so that cycles through. Those nutrients that we get the non-mineral nutrients, carbon, hydrogen, and oxygen, and the plants get those through their air and water. And then the mineral nutrients, well, those are absorbed through the roots as solutes in water, and those primaries are nitrogen, phosphorus, and potassium. And we're going to study, we have that in red there, the phosphorus. And then other nutrients that we could study would be secondary nutrients, calcium, magnesium, and sulfur, or the longer list at the bottom is micronutrients. So those are needed in much less amounts, very small amounts, but they can be very significant. I've seen where addition of sulfur through fertilizer has changed alfalfa field from being non-productive to productive. All right, there's a couple other things that go with having phosphorus present. Just because we have phosphorus present doesn't mean, or we have put it on the soil, it's actually usable. One of the things is you need water, all right? And so you have to have soil that percolates, all right, that water can move through. If we actually move it through too much, then, or too much water gets moved through the soil, we can actually leach the nutrients out of it. And so there's a balance, and when we apply becomes important too. Another big factor in terms of the soil and phosphate availability is the pH, right? And so the pH of the soil is hugely significant. For most plants, the soil needs to be between about 5.5 to about 7.5 for the phosphorus to be available to them. There's some plants that like more acidic or basic soil, but in general, it's right around that 6 to 7 pH, which is ideal. So we actually change the pH of the soil by putting in a buffer, and we put out ag-lime to change that pH. Now, in an agricultural setting, we would use trucks to spread that to make that happen in such a way. And so anyway, due to pH, they're unavailable, or they can leach during rain events or when we do excessive irrigation. So we need to try to make sure that we have enough water that we grow, enough water we have a small amount of runoff, but not so much that we leach the soil. We want to adjust the pH to 6 to 7 to make it ideally usable. And so those are some strategies to make your fertilizer work better. If you have a pH which is inappropriate, the plants can't use it, then there would be no purpose in spreading it. So those things are all important in this relationship. Now, fertilizer, we go and purchase that, right? We can buy it at a farm supply or from a specific fertilizer dealer, or even in our hardware store for our lawns. And there are three numbers that are given on a bag of fertilizer. And so the potassium, the nitrogen first, the phosphorus, and then the potassium. And so those are telling us the amounts that are present. The nitrogen actually is specifically in the percent nitrogen. So this fertilizer has 6% nitrogen, and then it has 12% of it is phosphate as P2O5. So that means that it isn't all phosphate, right? That there's oxygens involved in that. And so if you want to know the amount of phosphate specifically, then you would have to do a mole calculation to find that. And then the same thing with the potash or the potassium, right? The potassium comes as K2O. And so if we wanted to know specifically the amount of calcium or potassium present, then we would have to calculate that through a stoichiometric calculation. And so this discussion over here goes through that if you want to review with some other fertilizers. And so anyway, and it talks about how it's actually measured and those types of things. We're not measuring the phosphorus as P2O5, we're going to measure it as the magnesium ammonium phosphate hexahydrate. And we talk about that reaction on the first slide. And so anyway, we'll have to do some math to make sure we're comparing apples to apples. I asked you in the handout to go to phosphorus for both the commercial number and for the gravimetric precipitation. So we're going to compare those apples to apples through math. And so what I suggest, this is just to help you do the math. If you, for example, start with 3 grams of your commercial fertilizer, remember that if it's 12% P2O5, and so if you multiply the 3 grams times the 12%, you would get 0.36 grams of P2O5. That's the amount of that in your fertilizer. And then you have to do a mole conversion. So you would take the 0.36 grams of P2O5, convert that to moles of P2O5, and then there's, for every 1 P2O5, there's 2 phosphorus. And so you would do that conversion to moles of phosphorus, and then use the atomic weight of phosphorus to get back to grams. And so your bag would give you the theoretical grams of phosphorus that would be present in 3 grams, okay? So for the next calculation, you're actually going to do a reaction where you're going to make the magnesium ammonium phosphate hexahydrate, and you're going to take that, find its molecular weight, convert it to moles, and then for every 1 mole of this compound, there's 1 mole of phosphorus, and then you're going to find the grams of experimental phosphorus. Once you have the grams of each of those, then you could calculate the percent phosphorus, or what I want you to do is to compare the grams of experimental to theoretical. And so what I want you to do is take the absolute value of the experimental mass minus the theoretical mass and divide that by the theoretical mass. And so that will give you a percent error from that number. And so we're going to do that to compare the label value to what you actually measure, okay? So that's the gist of the lab. This week we're going to wear safety glasses, and our reagents for this week can actually be disposed down the drain, okay? So I'm looking forward to seeing you in lab. Good luck on your quiz, and have a great day.